Look up at the night sky, and you're staring into an ocean of unanswered questions, a vast, swirling expanse where the rules of reality seem to bend and twist in ways we're only beginning to understand. Out there, beyond the familiar glitter of stars, lies a galaxy so mesmerizing, so packed with enigmas, that it challenges everything we think we know about the cosmos. Welcome to NGC 1300, a barred spiral galaxy 65 million light-years from Earth, where the ordinary gives way to the extraordinary. Picture this: a colossal pinwheel of stars, dust, and dark matter, its arms stretching outward like cosmic tentacles, each one hiding secrets that defy explanation. But what makes this galaxy so special? Why does it captivate astronomers and stargazers alike? Because nestled within its swirling depths are 30 bizarre phenomena, unexplained flashes of light, mysterious radio signals, even the whispered possibility of structures that shouldn't exist. This isn't just a tour of another galaxy. It's a journey into the unknown, where every discovery raises more questions than answers. Imagine standing on the edge of NGC 1300, gazing into its heart, a luminous bar of stars cutting through its center, a feature so rare and striking that it makes this galaxy a cosmic oddity. That bar isn't just for show, it's a gravitational powerhouse twisting the very fabric of space around it, shaping the orbits of billions of stars. And yet, despite its grandeur, what truly sets this galaxy apart are the anomalies that lurk in its shadows. Strange energy bursts that flicker like cosmic Morse code, unexplained voids where stars vanish without a trace, even whispers of gravitational waves rippling in patterns that shouldn't be possible. Each one of these phenomena is a puzzle piece in a mystery spanning millions of years, and we're only just starting to put them together. But why should you care about a galaxy so far away that its light left when dinosaurs still roamed the Earth? Because NGC 1300 isn't just a distant spectacle, it's a mirror. What we learn here could rewrite the rules of physics, reshape our understanding of black holes, or even reveal clues about the origins of the universe itself. This isn't just about observing strange occurrences, it's about unraveling the fabric of reality. So buckle up, because over the next 30 revelations, we're diving deep into the heart of this galactic enigma, uncovering truths that will leave you questioning everything you thought you knew about space. The journey begins now. Deep within the swirling chaos of NGC 1300, something impossible flickers in and out of existence, spiral arms that shouldn't be there. Most galaxies wear their structure like a permanent fingerprint, their arms etched into the cosmos for eons. But here, astronomers have caught glimpses of faint, ghostly limbs that materialize in observations only to vanish without explanation. These phantom arms don't follow the rules. They pulse like a cosmic heartbeat, emerging in some wavelengths of light while remaining utterly invisible in others, as if the galaxy itself is playing hide and seek with the universe. What could possibly cause such a bizarre phenomenon? The leading theories sound like something ripped from a science fiction novel. Some researchers point to dark matter, that mysterious, invisible substance making up most of the universe's mass, suggesting dense clumps of it might be warping the galaxy's structure like invisible hands molding clay. Others propose these arms are cosmic mirages, created by gravitational lensing so extreme it bends light into shapes that deceive our telescopes. Then there's the wild card, ancient, unstable black holes lurking just beyond detection, their gravitational tugs twisting the galaxy's fabric in ways we can't yet predict. But here's the real twist: these phantom arms might be more than just a celestial curiosity. If they're driven by dark matter, their behavior could finally give us clues to unlocking one of the universe's greatest mysteries. And if they're proof of gravitational forces we've never seen before, well, that would mean our textbooks are missing entire chapters on how galaxies live and breathe. Every flicker of these ghostly arms is a whisper from the cosmos, challenging us to listen harder, look deeper, and admit just how much we still don't understand. At the heart of NGC 1300, something isn't adding up. Every massive galaxy is supposed to have a supermassive black hole, a ravenous beast millions of times heavier than our Sun, devouring everything that strays too close. These cosmic monsters usually announce their presence with screaming jets of energy, violent outbursts of X-rays, and swirling disks of superheated gas. But NGC 1300's black hole, it's almost polite. Unlike the chaotic, energy-spewing behemoths at the centers of galaxies like Andromeda or Messier 87, this one sits in eerie silence, emitting barely a whisper of the radiation it should. It's as if someone hit the mute button on a cosmic hurricane. So why is this black hole so shockingly quiet? One theory suggests it's starving. Black holes feed on gas and dust, and if the material around it has thinned out, it might simply have nothing left to consume. But here's the catch: NGC 1300's spiral arms are rich with star-forming regions, bursting with fresh gas clouds. There's no shortage of fuel. Another possibility: this black hole isn't dormant, it's discrete. Some astronomers speculate it might be expelling energy in ways we can't easily detect, perhaps through faint, slow-moving jets or subtle gravitational waves that slip past our instruments. Then there's the most tantalizing idea of all. What if this black hole isn't just quiet but fundamentally different? Most supermassive black holes follow predictable patterns, but NGC 1300's outlier could be rewriting the rules. Maybe it spins slower than its counterparts, or its magnetic fields suppress its outbursts. Or perhaps, and this is where it gets truly bizarre, something inside the galaxy is actively suppressing it, like an unseen force keeping the beast on a leash. Whatever the reason, this cosmic anomaly forces us to question what we really know about how black holes behave. If we can unravel why this one refuses to roar, it might reveal secrets about how galaxies evolve, and what happens when the universe's most violent engines decide to take a nap. Now we come to one of NGC 1300's most head-scratching riddles, the case of the vanishing hydrogen. In most spiral galaxies, vast reservoirs of neutral hydrogen gas linger in their outer edges, a cosmic fuel tank for future star formation. But when astronomers trained their radio telescopes on NGC 1300's outskirts, they found something startling: empty space. Where there should have been enough hydrogen to birth billions of stars, there was barely a trace. It's like opening a pantry expecting shelves stocked with ingredients, only to find it stripped bare. So where did it all go? One possible culprit is the galaxy's fierce stellar winds. Young, massive stars in its spiral arms blast out radiation and charged particles at nearly the speed of light, potentially blowing the lightweight hydrogen gas clean out of the galaxy's gravitational grip. Another theory points to the galaxy's barred structure. That prominent central bar may act like a cosmic plow, funneling gas inward so aggressively that the outer regions were left depleted over eons. But here's where things get even stranger. Without that hydrogen, NGC 1300's outer realms should be a stellar graveyard, devoid of new star formation. Yet recent infrared surveys reveal something unexpected: faint, sporadic bursts of stellar birth flickering in these supposed dead zones. It's as if the galaxy is defying its own rules, creating stars without the necessary fuel. Some astronomers suggest rogue gas clouds, too sparse for our telescopes to detect individually, might be secretly drifting in. Others wonder if an ancient collision with a smaller galaxy ejected hydrogen in chaotic patterns we're only now glimpsing. This missing hydrogen mystery isn't just academic, it challenges our fundamental models of how galaxies evolve. If NGC 1300 can form stars against all odds, what else have we gotten wrong about the life cycle of spiral galaxies? Every unanswered question here forces us to rethink the delicate balance between gas, gravity, and the birth of stars. And that's what makes this enigma so thrilling. It's not just about what's absent, but what its absence reveals about the universe's hidden playbook. Just when astronomers thought they had NGC 1300 figured out, the galaxy throws another curveball: starbursts that erupt like cosmic fireworks in all the wrong places. Most galaxies follow a predictable rhythm of star formation, with new suns igniting steadily along their spiral arms. But here, massive clusters of young stars flare up in chaotic bursts, scattered across regions where the conditions for stellar birth should be utterly inhospitable. It's as if the galaxy is scribbling outside the lines of every astronomy textbook. What makes these starbursts so baffling isn't just their location, it's their timing. Unlike the steady, billions of years-long processes we see in other spiral galaxies, NGC 1300 star-forming frenzies seem to start and stop on a whim. One patch of space might lie dormant for eons, then suddenly explode with the birth of thousands of stars in a geological blink of an eye. Some of these stellar nurseries glow with the intensity of newborn suns, while others flicker out almost as quickly as they appeared. Theories abound, but none fully explain the chaos. One camp argues these bursts are triggered by shock waves rippling through the galaxy, perhaps from ancient supernova or collisions with rogue gas clouds. Others point to NGC 1300's unusual barred structure, suggesting its central star bar acts like a pendulum, rhythmically compressing gas pockets until they ignite in sporadic fireworks. Then there's the radical idea that dark matter filaments weaving through the galaxy's core might be funneling hidden reservoirs of gas into sudden, violent collapses. But the real puzzle isn't just how these starbursts happen, it's what they mean for galactic evolution as a whole. If stars can form in such erratic, unpredictable ways, our models of how galaxies age might need a complete overhaul. Imagine a forest where trees sprout in explosive groves overnight instead of growing steadily over centuries. That's the kind of cosmic rule breaking we're witnessing here. Every anomalous starburst in NGC 1300 isn't just a spectacle, it's a challenge, pushing us to rethink the very timeline of how galaxies live, breathe, and light up the darkness. NGC 1300 has a trick up its sleeve, one that bends reality itself. When astronomers peered at this galaxy's outer edges, they noticed something odd. Distant background galaxies didn't look quite right. Their light stretched and warped, not in the smooth arcs typical of gravitational lensing, but in jagged, uneven distortions, as if space-time itself had developed a kink. This wasn't just a cosmic funhouse mirror, it was a full-blown gravitational mirage, hinting at hidden masses lurking where our telescopes see nothing at all. Gravitational lensing usually acts like a predictable magnifying glass. Massive objects like galaxy clusters bend light from objects behind them into elegant rings or arcs. But NGC 1300's lensing effect is messier, more chaotic. Some background stars appear duplicated in disjointed fragments, while others smear into faint, asymmetrical smudges. The patterns suggest an invisible scaffold of mass, not just the galaxy's visible stars and gas, but something else warping the fabric of space in ways we can't directly observe. So what's really causing this cosmic hall of mirrors? The prime suspect is dark matter, but not the smoothly distributed kind most models predict. Here, the distortions imply clumps and filaments of unseen mass tangled around the galaxy's outskirts like a spider's web. Some researchers speculate these could be the remnants of ancient dwarf galaxies, long since torn apart and digested by NGC 1300's gravity, leaving only their dark matter skeletons behind. Others propose a wilder idea, that we're seeing the fingerprints of primordial black holes scattered like invisible anchors in the galaxy's halo. But the real puzzle is what this means for our understanding of gravity itself. If these distortions stem from dark matter behaving in ways we've never mapped, it could force us to rethink how matter clumps together across the universe. Or worse, what if our equations for gravity are incomplete? Every twisted image in this gravitational mirage isn't just a curiosity. It's a potential crack in the foundation of modern physics waiting to be explored. Out in the cosmic orchestra of spiral galaxies, NGC 1300 is the mysterious musician refusing to play its part. Most galaxies of its size blast radio waves into the void like roaring brass sections, jets from supermassive black holes, the crackle of supernova remnants, the hum of star-forming regions. But this galaxy, it's stuck on mute. Despite its sprawling arms and bustling stellar nurseries, NGC 1300 emits radio signals so faint they border on undetectable. It's as if someone flipped a cosmic switch, silencing a symphony mid-performance. This radio silence isn't just quirky, it's downright baffling. Take its galactic cousins like Messier 81 or Andromeda. Their radio emissions paint vivid soundscapes, tracing magnetic fields and violent stellar births. Yet scans of NGC 1300 reveal only whispers, a ghostly static that defies expectations. What could stifle a galaxy's voice so completely? One clue lies in its magnetic fields. Radio waves often amplify around turbulent magnetic structures, but here, measurements suggest an eerie smoothness, as if the galaxy's magnetic fabric has been ironed flat. Some researchers speculate its central black hole's unusual quietude plays a role without the chaotic energy injections typical of active galactic nuclei. There's nothing to energize the surrounding plasma into radio-bright frenzies. But the plot thickens when you peer deeper. Infrared observations reveal NGC 1300 star-forming regions are just as lively as those in noisier galaxies, churning out young, massive stars that should be crackling with radio emissions. So why the hush? One radical theory suggests a cosmic balancing act. Perhaps the galaxy's interstellar medium is so efficiently tuned that it absorbs or scatters radio waves before they can escape, like a sponge soaking up sound. Others wonder if past collisions stripped away the charged particles needed to amplify these signals, leaving the galaxy in a peculiar electromagnetic drought. The implications ripple far beyond this single anomaly. If NGC 1300's silence stems from some unknown galactic feedback mechanism, it could rewrite how we understand energy circulation in spiral galaxies. Or worse, what if our assumptions about radio emissions are fundamentally flawed, and this galaxy isn't the outlier but a glimpse of a rule we've yet to uncover? Every muted frequency from its depths isn't just a gap in data, it's a question etched into the static, waiting for an answer. In the cosmic rulebook of supermassive black holes, relativistic jets are practically mandatory. Twin beams of plasma screaming into space at nearly light speed, powered by the black hole's insatiable appetite. These jets sculpt entire galaxies, trigger star formation, and light up the universe with high-energy radiation. Yet in NGC 1300, the central black hole breaks this cardinal rule. Despite its staggering mass, millions of times that of our Sun, it sits in baffling stillness, its expected jets conspicuously absent. It's the cosmic equivalent of a volcano that refuses to erupt, leaving astronomers scrambling for answers. What could possibly muzzle such a powerful force of nature? The leading suspect is an invisible cage of magnetic fields, normally a black hole's accretion disk. The swirling maelstrom of doomed matter generates tangled magnetic fields that act like particle accelerators, launching jets outward like cosmic fire hoses. But in NGC 1300, observations suggest these fields might be strangely orderly. Their lines bundled too tightly to allow the explosive release of energy required for jet formation. Picture trying to light a firework wrapped in layers of duct tape. No matter how much energy you pack inside, it can't explode the way it should. But magnetic strangeness isn't the only clue. The black hole's diet could be playing a role. Jets typically thrive on chaotic feasting gulps of gas and stars devoured in erratic bursts. Yet spectral analysis hints this black hole might be dining more like a gourmet than a glutton, consuming material in a slow, steady trickle too meager to power the usual outburst. There's also the eerie possibility that the galaxy itself is starving its central monster. Some models suggest NGC 1300's unique barred structure funnels gas away from the core, leaving the black hole perpetually underfed. The implications ripple far beyond this single galaxy. If magnetic suppression proves true, it could mean we've underestimated how often black holes operate in stealth mode across the universe. And if the answer lies in the galaxy's structure, that rewrites our understanding of how galaxies and their black holes co-evolve. Every silent moment from this cosmic anomaly isn't just a gap in data, it's a challenge to the very foundations of astrophysics, daring us to rethink how black holes shape the cosmos. If dark matter were a shadow, NGC 1300 should be a perfect silhouette, smooth, symmetrical, hugging the galaxy like a second skin. Instead, it's more like a tattered cloak full of unexpected lumps and gaps. Astronomers have mapped the galaxy's dark matter halo using the subtle wobbles of orbiting stars and the bending of distant starlight, expecting to find the classic, fluffy sphere predicted by simulations. What they uncovered is anything but textbook. The halo is lopsided, denser on one side than the other, with strange tendrils extending into the void like cosmic roots searching for water. This asymmetry isn't just a visual oddity, it's a direct challenge to our understanding of how dark matter behaves. According to the cold dark matter model, halos should form through gentle mergers over billions of years, resulting in balanced, almost featureless structures. Yet NGC 1300's halo looks more like the aftermath of a cosmic bar fight, with clumps and voids that suggest violent, recent collisions. Some researchers argue this could mean dark matter interacts with itself more than we thought, creating friction that distorts its shape. Others propose an even wilder idea, that certain types of dark matter might decay over time, leaving behind these patchy remnants. But the most tantalizing clue lies in the halo's filamentary streaks. These wispy extensions align eerily with the paths of nearby dwarf galaxies, as if they're gravitational breadcrumbs left behind from ancient galactic feasts. If confirmed, it would mean NGC 1300 is still digesting smaller neighbors, their dark matter smeared across space like jam on toast. That would make this halo a living record of the galaxy's violent history, written in invisible ink. The implications stretch far beyond this single galaxy. If dark matter halos can be this irregular, it might explain why so many galactic collisions look messy and unpredictable, and if dark matter truly interacts or decays. That could rewrite the rules for everything from galaxy formation to the ultimate fate of the universe. Every lump in this halo isn't just a curiosity, it's a potential key to unlocking the nature of the cosmos' most elusive substance. Somewhere in the depths of NGC 1300, invisible fireworks keep detonating gamma-ray flares so intense they briefly outshine entire galaxies, yet leave no trace of their origin. These bursts aren't just random, they pulse with eerie regularity, flickering like a cosmic strobe light before vanishing without explanation. Gamma rays, the universe's most energetic light, usually come with a built-in receipt: supernova explosions, colliding neutron stars, or the violent appetites of black holes. But here, the usual suspects are nowhere to be found. It's as if the galaxy itself is leaking radiation from a hidden dimension. The leading theory sounds like something from the edge of physics: dark matter annihilation. If dark matter particles, whatever they are, collide and destroy each other, they could theoretically unleash gamma rays in these exact sporadic bursts. NGC 1300's lopsided dark matter halo, with its clumps and tendrils, might be the perfect breeding ground for such rare interactions. Imagine throwing two invisible rocks into a pond. The ripples they'd make when they collide would be the only hint they ever existed. That's what astronomers are searching for in these gamma-ray patterns, the faintest echo of dark matter's true nature. But there's a twist. Buried in the data are hints of structure, subtle repetitions in timing that don't quite fit the dark matter decay narrative. Some researchers argue these flares could be from pulsars, rapidly spinning neutron stars cloaked in such dense clouds of dust that their usual radio beacons are completely muffled. These hidden pulsars might only reveal themselves through occasional gamma-ray screams when magnetic storms rip through their atmospheres. It's like hearing a scream in a fog bank, the source obscured but the violence unmistakable. Yet the most tantalizing possibility remains uncharted territory, something entirely new. Gamma rays shouldn't appear without a clear engine, yet NGC 1300 seems to defy that logic. Could there be exotic physics at play, like miniature black holes evaporating or quantum foam fluctuations? Every unexplained pulse forces us to confront how little we truly understand about the high-energy universe. These flares aren't just anomalies, they're flares of a different kind, beacons in the dark, urging us to look deeper, question harder, and admit that some of the cosmos' loudest screams might still be whispers in the void. NGC 1300's bar shouldn't exist, at least not according to our best simulations. Galactic bars, those striking lanes of stars cutting through a spiral's core, are cosmic tightropes. They balance billions of stars in perfect tension, yet even the slightest gravitational nudge should send them unraveling into chaos. Most models predict these structures fragmenting within a few billion years, their stars scattering like marbles dropped on a slope. But NGC 1300's bar has defied the odds, holding steady for over 8 billion years, twice as long as theory allows. It's as if someone nailed the universe's most delicate mobile in place, freezing it mid-swing against all logic. What's holding this cosmic balancing act together? The answer might lie in the galaxy's dark matter skeleton. While most barred spirals rely on the gravity of visible stars to maintain their shape, NGC 1300's lopsided dark matter halo could be acting like an invisible scaffold. Simulations suggest its uneven distribution creates gravitational anchors, pockets of stability that prevent the bar from wobbling itself apart. Picture a spinning top. Normally, it would topple quickly, but if you could warp the surface beneath it just right, it might spin indefinitely. That's the kind of fine-tuned cosmic engineering we're witnessing here. But dark matter isn't the only suspect. The bar's own stars might be conspiring to keep it intact. Recent studies reveal an unexpected pattern. Older, metal-rich stars clustered along the bar's edges, acting like gravitational bookends. These ancient suns, heavier and more tightly bound than their younger counterparts, could be providing just enough extra mass to dampen destructive vibrations. It's a galactic feedback loop. The bar's stability allows these stars to settle into place, and their presence, in turn, reinforces the bar. Yet the strangest twist comes from the bar's rotation. Unlike most galactic bars, which slow down as they age, NGC 1300 spins at nearly its original breakneck speed. Some researchers point to the galaxy's sparse outer gas reserves as the culprit. Without much external material to drag against, the bar experiences less friction, like a figure skater pulling in their arms to spin faster. Others argue the bar might be stealing angular momentum from the galaxy's dark matter halo, an invisible energy transfer that keeps it revving like a cosmic engine. The implications ripple far beyond this single galaxy. If bars can survive this long, entire models of galactic evolution need revisiting. Maybe bars aren't temporary features but the backbones of spiral galaxies, shaping their destinies for eons. Or perhaps NGC 1300 is the exception that proves the rule, a cosmic fluke that's quietly rewriting the textbooks. Either way, every steadfast rotation of this ancient structure whispers a challenge to our understanding of how galaxies grow old. Among the countless stars swirling through NGC 1300 spiral arms, a handful of ancient wanderers stand out, globular clusters that don't belong. These dense balls of stars, each packed with hundreds of thousands of suns, orbit the galaxy like celestial strays, their ages telling a story that doesn't match their current home. While most of NGC 1300 stars are relatively youthful, these clusters are cosmic elders, their origins dating back to the universe's chaotic infancy. It's as if someone dropped antique jewels into a modern art exhibit, their presence raising a single, irresistible question. How did they get here? The answer might rewrite the galaxy's history. Globular clusters typically form alongside their parent galaxies, emerging from the same primordial gas clouds. But these orphaned clusters are too old by billions of years to have originated within NGC 1300. Their very existence points to a violent past, a time when this galaxy wasn't spinning in isolation, but was locked in a gravitational tug of war with another. Astronomers trace their paths backward, and the math paints a dramatic picture. A smaller galaxy, long since devoured, its stars assimilated into NGC 1300 spiral arms, leaving only these clusters behind as cosmic breadcrumbs. What makes these clusters even stranger is their resilience. Galactic mergers are messy affairs, with tidal forces shredding most structures apart. Yet these globular clusters have survived untouched, their tight-knit stellar communities resisting dissolution. Their orbits hold clues to some loop in wildly inclined paths far from the galaxy's disk, as if flung there during the chaos of collision. Others hover near the edges of NGC 1300's dark matter halo, suggesting they were once the central jewel of the devoured galaxy, now adrift in a foreign gravitational field. But the real mystery isn't just where these clusters came from, it's what they're hiding. Ancient stars like these are time capsules, preserving the chemical fingerprints of the early universe. Unlike younger stars forged from recycled gas enriched by generations of supernova, these relics contain almost no heavy elements, offering a pristine snapshot of cosmic conditions before galaxies like ours even existed. Studying them is like cracking open a geological core sample, each layer revealing secrets about the universe's formative years. The implications stretch far beyond a single merger. If NGC 1300 swallowed a galaxy to collect these clusters, how many other spirals have hidden histories written in stolen starlight? And if these clusters can survive billions of years intact, could they be the key to understanding how galaxies grow through cosmic cannibalism? Every orphan cluster circling this galaxy isn't just a relic, it's a silent witness to the universe's most dramatic transformations, waiting for us to decipher its story. Hidden within the luminous bar of NGC 1300, where stars crowd together like commuters in a cosmic subway, lies a dusty enigma that defies the laws of galactic traffic. These dark ribbons of interstellar dust, usually content to drift lazily along with the flow of stars, are instead caught in a celestial counter-current, streaming backward against the galaxy's rotation like salmon fighting their way upstream. This isn't just an oddity, it's a full-blown revolt against the gravitational order, one that could rewrite our playbook for how spiral galaxies evolve. Dust lanes are supposed to be predictable. In most barred galaxies, they funnel obediently toward the center, riding the gravitational slipstream created by the bar's relentless spin. But here, high-resolution images from the Hubble and ALMA telescopes reveal something startling. Patches of dust spiraling outward, their movement etched in the faint shadows they cast against the glow of background stars. It's as if someone hit rewind on a portion of the galaxy, sending matter the wrong way through its cosmic conveyor belt. The effect isn't uniform. Some dust drifts normally, while neighboring filaments seem caught in an invisible eddy, creating a patchwork of conflicting motions that leave astronomers scratching their heads. Theories to explain this paradox range from the elegant to the exotic. One camp suggests the galaxy's central black hole, though eerily quiet now, might have had a violent tantrum in the distant past. A past outburst could have sent shockwaves rippling through the bar, temporarily reversing gas flows and leaving behind these rebellious dust lanes as cosmic aftershocks. Others point to NGC 1300's lopsided dark matter halo, proposing its uneven gravity might be twisting the bar's internal dynamics like a spoon stirring honey, creating zones of backward flow. But the most tantalizing explanation involves resonance, a concept borrowed from music. Just as a perfectly timed push can keep a swing moving higher, certain gravitational frequencies within the bar might be amplifying tiny motions into full BLOW and Chinese letter currents. Computer simulations show that under precise conditions, the interplay between the bar's rotation and the galaxy's overall spin can set up standing waves that literally push dust the wrong way. If confirmed, this would mean NGC 1300 isn't broken, it's humming a harmony we've only just begun to hear. What makes this dust lane paradox truly revolutionary isn't just the mechanics, it's the implications. If dust can flow backward, entire models of how galaxies redistribute material, build their central bulges, and even feed their black holes might need revisiting. Picture a factory where some conveyor belt suddenly started running in reverse, dumping raw materials back onto the loading dock. That's the kind of cosmic recalibration we're facing. Every errant wisp of dust in this galaxy's bar isn't just a curiosity, it's a clue to forces shaping galaxies far beyond our own. Deep in the heart of NGC 1300, where temperatures should soar into the millions of degrees and space itself should sizzle with X-rays, there's nothing, a chilling absence. Every supermassive black hole we've ever studied sits at the center of a blazing corona of hot gas. Its accretion disk churning out X-rays like a cosmic lighthouse. But this galaxy's central monster defies the script. Observations from orbiting X-ray telescopes reveal a void so profound it's as if someone carved out the very radiation that should be there. The silence isn't just puzzling, it's rewriting our understanding of how black holes interact with their surroundings. Picture the scene, a black hole weighing millions of suns, surrounded by swirling gas that should be glowing fiercely as it spirals toward oblivion. This process, called accretion, is universal. The friction alone should heat the gas to temperatures rivaling the sun's core, making it shine brightly in X-rays. Yet when we peer at NGC 1300's core, the detectors register less than 1% of the expected signal. It's like watching a blazing fire reduced to embers with no explanation for where the heat went. So where is the X-ray glow hiding? One radical theory suggests the black hole might be expelling more energy than it absorbs. Normally, accretion disks lose energy as radiation, but here the energy could be channeled into powerful outflows, invisible gusts of particles moving so fast they carry the heat away before it can radiate. Think of it like a steam whistle on a boiling kettle. If the steam escapes fast enough, the kettle itself stays surprisingly cool. Some simulations show magnetic fields near the black hole might act like cosmic railguns, accelerating particles outward with such efficiency that little energy remains to glow in X-rays. But there's another, even stranger possibility. The gas might not be falling inward at all. Detailed spectroscopy hints the material around this black hole could be orbiting in a stable, almost lazy pattern, never getting close enough to heat up dramatically. If true, it would mean NGC 1300's black hole isn't just quiet, it's isolated, cut off from its fuel supply by some unseen barrier. The galaxy's unusual barred structure might be to blame, its gravitational fields acting like a cosmic dam, redirecting gas flows before they reach the center. The implications ripple far beyond this single anomaly. If black holes can operate without the telltale X-ray signatures we rely on to detect them, how many others have we missed? And if accretion disks can stabilize in these bizarre configurations, what does that mean for our models of galaxy evolution? Every unanswered question about this X-ray void isn't just a gap in data. It's a window into the black hole's most elusive behaviors, waiting to change how we see the darkest corners of the universe. Most galaxies wield their magnetic fields like gentle brushes, painting invisible lines of force that guide gas clouds into the graceful swirls of star formation. But NGC 1300's magnetic fields, they're more like a tangle of live wires, twisted into knots so severe they've become cosmic roadblocks, stifling the birth of new stars where there should be stellar nurseries in overdrive. This isn't just a quirk, it's a full-scale rebellion against the galactic norm, one that could explain why this galaxy's star formation lags behind its spiral siblings. Mapping these magnetic contortions required instruments sensitive enough to detect the faintest whispers of polarized light. What they revealed was astonishing. While most galaxies organize their magnetic fields along their spiral arms like railroad tracks, NGC 1300's field lines loop and crisscross in chaotic braids, especially near its central bar. In some regions, the fields even double back on themselves, creating pockets where gas clouds are too magnetized to collapse into stars. It's as if the galaxy has built-in stellar birth control, its own magnetic fingers pressing pause on star formation. The root of this cosmic knot might lie in the galaxy's turbulent past. Some astronomers speculate that NGC 1300 endured a near-miss collision with another galaxy billions of years ago, a gravitational sideswipe powerful enough to stir its magnetic fields like spoon strokes in thick batter, leaving them permanently scrambled. Others point to the supermassive black hole's unusual dormancy. Without the energetic jets typically unleashed by active black holes to comb the fields back into order, they've been left to tangle like unspooled yarn. But the real surprise came when researchers simulated these twisted fields. The models showed something startling. Where magnetic chaos reigns, gas clouds fragment into smaller, magnetically locked clumps, too stubborn to coalesce into stars. This could explain why parts of the galaxy teem with gas yet produce few new suns, a paradox that's baffled astronomers for years. In essence, NGC 1300's magnetic fields aren't just odd, they're actively strangling its stellar potential. Yet there's a silver lining to this cosmic snarling. By studying these magnetic knots, scientists might have stumbled upon a missing link in galactic evolution. If twisted fields can suppress star formation, they could explain why some galaxies age gracefully, conserving their gas over eons, while others burn out in brief, fiery bursts of stellar birth. NGC 1300's magnetic rebellion might just hold the key to understanding one of the universe's quietest mysteries: how galaxies decide when to light up the cosmos and when to stay in the dark. In the annals of cosmic oddities, few things unsettle astronomers like a supernova that cheats death, or at least leaves no corpse behind. NGC 1300 holds one such ghost in its stellar archives. Back in 2005, telescopes caught the unmistakable flash of a dying star within this galaxy, a brilliant supernova erupting with enough energy to outshine millions of suns. Yet when the light faded, something unprecedented happened. Nothing, no neutron star, no black hole, not even a wisp of expanding debris. It was as if the star had vaporized completely, leaving behind only a cosmic shrug where a stellar remnant should have been. Supernova don't just vanish. These violent explosions are nature's way of recycling star stuff, scattering heavy elements across space while leaving behind dense, compact relics. But NGC 1300's Phantom Supernova defies this script. Follow-up observations with Hubble and Chandra X-ray Observatory scoured the blast site, expecting to find at least a flicker of radiation from a newborn pulsar or the shadowy silhouette of a black hole's accretion disk. Instead, they found eerie silence, the leading theory this might have been a failed supernova, a rare event where the collapsing star's core doesn't just form a compact object, it disintegrates entirely. Imagine a building collapsing in on itself, only for the rubble to dissolve into thin air before it hits the ground. That's the kind of physics-bending scenario researchers are grappling with. One possibility involves exotic particles called sterile neutrinos, hypothetical relatives of the neutrinos we know, which could carry away so much energy that the core essentially evaporates. Another idea points to quantum vacuum decay, a catastrophic rearrangement of spacetime itself at the subatomic level, where the star's core doesn't collapse so much as unravel into nothingness. But the plot thickens when you consider the supernova's light curve. Most stellar explosions brighten and fade in predictable patterns, but this one dimmed faster than models allow, as if the star had been drained of energy before detonating. Some astronomers suspect it might have been a zombie star, a white dwarf that partially exploded, then somehow stabilized, leaving behind a smoldering husk too faint to detect. Others propose the remnant might be hidden a black hole spinning so fast it flings infalling material away before it can glow brightly enough for us to see. The implications ripple far beyond this single event. If stars can explode without leaving traces, we might need to revise how we measure cosmic distances, since supernovae are vital standard candles for mapping the universe. And if core collapse can simply vanish, it could mean there's a whole population of black holes or neutron stars lurking undetected, their births never announced by the usual fireworks. NGC 1300's Phantom Supernova isn't just a curiosity, it's a cosmic whisper, hinting that even the most violent deaths in the universe might sometimes leave no fingerprints at all. NGC 1300's outer stars are misbehaving. They drift along orbits that shouldn't exist, their paths warped as if tugged by an invisible hand. Galactic dynamics are usually clockwork. Stars follow predictable trajectories shaped by the gravity of visible matter. But here, entire swarms of stars veer off course, their motions hinting at something massive lurking just beyond our telescope's reach. The math doesn't lie. Something unseen, weighing perhaps 1 billion suns, is yanking at this galaxy's fringe like a hidden puppeteer, the prime suspect. A dwarf galaxy cloaked in darkness. Most large galaxies like ours host entourages of smaller satellite galaxies, but searches around NGC 1300 have come up eerily empty. Not for lack of trying, deep sky surveys have scoured its outskirts, hunting for the faint glow of stars that might betray a hidden companion. Yet the gravitational fingerprints remain, etched into the skewed orbits of distant stars. This suggests a thief in the night, a dwarf galaxy so densely packed with dark matter that its few visible stars are drowned in shadow, making it nearly impossible to spot. But the plot thickens when you consider alternative explanations. Could this be a rogue clump of pure dark matter, unbound to any galaxy? Simulations of cosmic structure formation predict such free-floating halos left over from the universe's chaotic infancy. These dark mavericks would exert gravity without emitting a single photon, warping space-time like invisible boulders in a stream. If one drifted too close to NGC 1300, its gravitational ripples could perfectly explain the stellar anomalies we're witnessing. Then there's the wildcard scenario, an ancient galactic collision. The disturbed orbits might be scars from a near-miss encounter millions of years ago, a gravitational sideswipe that sent stars reeling like bowling pins. Some astronomers point to faint stellar streams, wisps of stars trailing into the void, as potential debris from this cosmic fender bender. Others argue the galaxy's lopsided dark matter halo could amplify these disturbances, turning a minor gravitational nudge into a full-blown stellar revolt. What makes this mystery so pivotal isn't just the what, it's the why. If a dark matter-dominated dwarf is the culprit, its extreme composition could force us to rethink how satellite galaxies form. And if it's a rogue dark clump, that would be the smoking gun proving such structures wander the cosmos unseen. Even the collision hypothesis holds weight, offering a live test case for how galaxies evolve through gravitational encounters. Every errant star in NGC 1300's outer realms isn't just drifting off course, it's pointing towards secrets that could rewrite the rules of cosmic companionship. Among the countless stars painting NGC 1300's spiral arms, a peculiar population stands out: red giants burning brighter and far more numerous than any model predicts. These swollen, aging stars, their outer layers puffed into cool crimson orbs, cluster in baffling densities along the galaxy's western rim, crowding the cosmos like an overgrown orchard of cosmic cherries. Red giants aren't rare, but this concentration defies every rule of stellar demographics, hinting at a mysterious acceleration of the galaxy's celestial life cycle. What makes this red giant swarm so perplexing isn't just their numbers, it's their location. Stars evolve along predictable timelines dictated by their mass, with sun-like stars taking billions of years to exhaust their hydrogen fuel before ballooning into red giants. Yet these crimson behemoths dominate regions rich with young blue stars, a pairing as unlikely as finding ancient redwoods sprouting in a field of saplings. Spectroscopic analyzers reveal another twist: their chemical fingerprints match the galaxy's youngest stellar populations, as if they aged decades in mere minutes while their siblings burned steadily. Theories to explain this anomaly range from stellar vampirism to cosmic contamination. Some astronomers propose these giants might be the products of binary star systems gone rogue, where one star siphoned mass from its companion, artificially inflating itself ahead of schedule. Others point to NGC 1300's chaotic magnetic fields, suggesting they could have funneled dense waves of interstellar gas into these regions long ago, triggering accelerated star formation that's only now yielding this premature harvest of aging stars. But the most tantalizing clue lies in their heavy element content. These red giants carry traces of metals usually forged in supernovae, yet their surroundings show no signs of recent stellar explosions. This suggests they might have formed from pre-enriched gas, perhaps stolen during a galactic collision eons ago. If true, their existence could rewrite the timeline of NGC 1300's past encounters, painting a picture of violent mergers that left behind more than just gravitational scars. The implications ripple far beyond stellar oddities. If stars can be coerced into aging prematurely, entire models of galactic evolution need recalibrating. And if this red giant excess stems from external contamination, it could mean galaxies exchange more than just raw materials during collisions. They might trade entire generations of stars, each carrying chemical messages from their original homes. Every crimson glow in this anomalous cluster isn't just a dying ember. It's a time capsule preserving secrets about how galaxies manipulate the very clocks of the cosmos. NGC 1300 might be hiding a cosmic secret, one so subtle that astronomers are still debating its existence. Recent observations suggest the galaxy could be wrapped in a polar ring, a rare and spectacular structure that would make it unlike most spirals we've ever seen. Picture this: a colossal hoop of stars, dust, and gas spinning perpendicular to the galaxy's main disk, encircling it like a celestial hula hoop. Such rings don't form naturally. They're usually the scars of a galactic cataclysm, the aftermath of a smaller galaxy torn apart and strung into orbit during a violent collision. The evidence is tantalizing but thin, a faint smudge of starlight arcing over the galaxy's poles, visible only in specific wavelengths. Most polar rings announce themselves boldly, their bright loops standing out against the darkness of space. But here, the signal is so delicate that some researchers argue it could just be an optical illusion, a trick of perspective where distant background galaxies align perfectly to mimic a ring. Others point to strange motions in the galaxy's outer gas clouds, their trajectories skewed as if something massive, perhaps the ghostly remains of a devoured companion, is still tugging at them from above and below. If this ring is real, it would rewrite NGC 1300's history. Galactic mergers are messy affairs, yet this one would have had to be exquisitely precise. The victim galaxy wouldn't have just collided, it would have been shredded into a near-perfect circle, its debris locked into an orbit 90 degrees off-kilter from the main disk. Such surgical destruction is rare, requiring a cosmic bullseye of timing, angle, and momentum. Even more intriguing, polar rings are fleeting. Gravity should dissolve them within a few billion years, meaning this one, if it exists, could be a relatively fresh wound, a snapshot of a cosmic smash-up still echoing through the galaxy. But the real mystery isn't just how this ring formed, it's what it's doing to the galaxy today. Polar rings aren't just fossils, they're active participants, funneling gas into bizarre orbits that can ignite starbursts or starve the central black hole. Some models suggest NGC 1300's quiet core and patchy star formation might trace back to this hidden structure, its gravitational whispers still shaping the galaxy's evolution. If confirmed, this phantom ring wouldn't just be a curiosity, it would be the missing key to understanding why this galaxy breaks so many rules. Until then, it remains a ghostly, maybe, a cosmic riddle waiting for sharper telescopes and bolder theories to unravel. Among the most baffling enigmas in NGC 1300 is the curious case of light that refuses to travel in straight lines. Observations reveal pockets where starlight bends and scatters unpredictably, not around massive objects as gravitational lensing would predict, but in seemingly empty voids. These anomalous dispersion patterns resemble the froth of a turbulent ocean, tiny, chaotic fluctuations that some theorists argue could be the first observable hints of quantum foam, the hypothesized bubbling texture of spacetime itself at unimaginably small scales. Quantum foam is the frontier where Einstein's smooth spacetime collides with the frenetic uncertainty of quantum mechanics. Theoretical physics suggests that at scales a trillion times smaller than an atom, spacetime might not be a continuous fabric but a seething mass of virtual particles and wormholes popping in and out of existence. While these fluctuations are too minuscule to detect directly, their cumulative effects could, in theory, leave fingerprints on light traveling across cosmic distances. NGC 1300's rogue photons, their paths inexplicably zigzagging as if pushed by invisible hands, might be the first whispers of this foam bubbling beneath reality's surface. Critics counter that more mundane explanations exist. Interstellar dust clouds laced with exotic metallic compounds could diffract light in unusual ways. Others point to weak magnetic fields twisting the trajectories of charged particles, which in turn scatter starlight, yet the patterns resist conventional modeling. The light doesn't just bend, it fractures into irregular spectra like sunlight passing through shattered glass. Intriguingly, these distortions cluster in regions where the galaxy's dark matter halo shows peculiar density variations, fueling speculation that dark matter and quantum foam might interact in ways we've yet to imagine. The most tantalizing data comes from polarized light studies. Some photons exhibit unexpected twists in their polarization angles, as if spacetime itself briefly rotated around them. If confirmed, this could imply that quantum foam isn't just a passive backdrop but an active participant, churning enough to leave detectable imprints on traversing light. Future telescopes capable of capturing even fainter signals might finally settle the debate, either unveiling a fundamental layer of reality or forcing us to invent entirely new physics to explain why this galaxy sees the universe through a broken lens. Nestled in the outskirts of NGC 1300, a cosmic metronome ticks at the wrong speed, a pulsar whose rhythmic radio pulses arrive slower than physics says they should. Pulsars are nature's most precise timekeepers, ultra-dense neutron stars spinning with such regularity that their beams of radiation sweep past Earth like lighthouse beams, predictable down to microseconds. But this particular pulsar, catalogued as PSR J03, 18-0643, defies expectations. Its pulses crawl along nearly 20% slower than similar pulsars of its age and spin rate, as if time itself stretches thin in its vicinity. At first glance, the explanation seems straightforward: extreme gravity. According to Einstein, clocks tick slower in stronger gravitational fields, an effect called time dilation. If this pulsar orbited an unseen companion like a black hole or quark star, the intense gravity could warp time enough to delay its pulses. Yet meticulous observations reveal no massive partner tugging at the star. Its motion through space is eerily smooth, with no wobble suggestive of a hidden dance partner. That leaves two possibilities, each more unsettling than the last. First, we might be witnessing a pulsar caught in the grip of an enormous concentration of dark matter. Simulations suggest NGC 1300's lopsided halo could harbor dense knots of dark matter massive enough to distort spacetime locally, creating pockets where time flows differently. If this pulsar drifts through such a knot, its signals would reach us delayed, like a radio broadcast passing through layers of thick fog. Alternatively, the pulsar itself could be fundamentally different. Most neutron stars are thought to be composed of hyperdense neutrons, but some theories predict exotic states of matter in their cores: free quarks, strange matter, or even prion condensates. These bizarre materials might alter how the star's magnetic fields generate pulses, effectively stretching each radio burst like taffy. Supporting this idea are subtle anomalies in the pulse's structure, unusual harmonics that suggest something inside the star is vibrating at frequencies no ordinary neutron star should produce. Yet the most radical explanation challenges our very understanding of time. Quantum gravity theories predict spacetime might become granular at microscopic scales, like the static on an old television screen. Normally, this graininess is imperceptible, but across 65 million light-years, its effects could accumulate, introducing tiny delays in the pulsar's signals. If true, this time-dilated pulsar isn't just an oddity, it's a lighthouse shining through the foam of spacetime itself, its flickers carrying encoded hints about the universe's most fundamental structure. Every slowed pulse from this cosmic anomaly forces us to confront how much we still don't understand about gravity, time, and the invisible scaffolding of reality. Whether it's dark matter, exotic physics, or something entirely new, one thing is certain: NGC 1300's wayward timekeeper is more than just a curiosity. It's a challenge written in the slow-motion Morse code of the cosmos, waiting for us to decipher its message. Deep within the swirling arms of NGC 1300, astronomers have stumbled upon a cosmic chemistry experiment gone rogue: pockets of space where the metal content spikes unpredictably, defying every rule of galactic mixing. In most spiral galaxies, heavy elements like iron, oxygen, and silicon spread relatively evenly over time, stirred by supernova explosions and stellar winds. But here, certain regions glitter with up to 3 times the expected metallicity, while neighboring zones remain stubbornly pristine. It's as if someone took a salt shaker to the galaxy, sprinkling extra metals in random patches while leaving the rest untouched. This metallicity mismatch isn't just a curiosity, it's a direct challenge to our understanding of how galaxies recycle their materials. Stars forge heavy elements in their cores and scatter them when they explode, enriching the surrounding gas for future stellar generations. Over billions of years, turbulence and rotation should blend these elements into a uniform cosmic soup. Yet NGC 1300's uneven distribution suggests something is disrupting the mixing process, preserving stark chemical boundaries like layers in a cake that refuse to dissolve. One clue lies in the galaxy's unusual barred structure. The central bar acts like a colossal blender, but instead of homogenizing the mix, it might be creating chemical eddies, regions where enriched gas gets trapped in gravitational whirlpools, piling up metals in dense pockets. Infrared observations reveal that the most metal-rich zones align with areas where the bar's gravitational forces compress gas into tight knots, as if the galaxy itself is corralling heavy elements into cosmic stockpiles. But the bar isn't the only culprit. Spectroscopic data reveals another bizarre pattern. Some metal-rich regions coincide with faint stellar streams, the ghostly trails left by smaller galaxies devoured long ago. These interlopers might have carried their own stockpiles of heavy elements, depositing them like cosmic paint splatters during violent mergers. Unlike gradual mixing, these sudden injections could leave abrupt chemical borders, especially if the ingested galaxy was unusually rich in metals to begin with. Then there's the wild card dark matter again. The galaxy's lopsided dark matter halo could be warping the flow of interstellar gas in ways that segregate metals. Picture a river contaminated with dye. Normally, the current disperses the color evenly, but if hidden boulders deflect the flow, patches of concentrated dye might linger. Similarly, clumps of dark matter might be redirecting metal-laden gas flows, creating pockets where elements accumulate against all odds. What makes this metallicity puzzle so pivotal isn't just the how, it's the so what. If galaxies can hoard heavy elements in isolated reservoirs, it changes how we model their chemical evolution. Suddenly, the ingredients for rocky planets or even life might not be evenly distributed but concentrated in celestial sweet spots. Every anomalous metal-rich zone in NGC 1300 isn't just a scientific oddity. It's a potential game-changer, revealing that the universe's periodic table might be far more unevenly and mysteriously spread than we ever imagined. NGC 1300's disk isn't the flawless spiral it appears to be. Peer closely, and you'll notice a subtle warp, as if the galaxy itself is bending under some unseen weight. Most spiral galaxies hold their shape with symmetrical precision, their disks flat and uniform like vinyl records spinning through the void. But here, the outer edges twist ever so slightly, the stars and gas tilting upward on one side and downward on the other, creating a shape reminiscent of a cosmic potato chip. This warping isn't just aesthetic, it's a cosmic clue, hinting at invisible forces tugging at the galaxy from beyond its borders. The prime suspect, an ancient encounter with vast intergalactic gas clouds, the ghostly remnants of a cosmic collision lost to time. Picture this: millions of years ago, NGC 1300 plowed through a diffuse sea of hydrogen, left behind by a long-vanished dwarf galaxy or a filament of the cosmic web. Though these gas clouds are nearly invisible, their collective mass could be staggering enough to exert a gravitational pull strong enough to warp the disk as the galaxy moved through them. It's like a ship cutting through water. The hull might flex under the pressure, even if the waves leave no lasting mark. But there's another, more tantalizing possibility. The warp could be evidence of a dark matter wake, an invisible ripple stirred up as the galaxy moves through its local universe. Dark matter doesn't just clump around galaxies, it forms vast, sprawling rivers between them. If NGC 1300 is sailing through one of these currents, the uneven tug of dark matter particles could be slowly distorting its disk, like wind reshaping a dune. Some simulations even suggest that dark matter subhalos, small, invisible clumps orbiting the galaxy, might be responsible, their gravitational nudges accumulating over eons into this subtle but unmistakable bend. What makes this warp so fascinating isn't just its origin, but its resilience. Normally, such distortions should smooth out over time as the galaxy's rotation and internal forces restore equilibrium. Yet NGC 1300's warp persists, defying the calming influence of its own gravity. This suggests the warping force isn't just a one-time event, it's ongoing, a constant pressure from an unseen hand. Recent radio observations add weight to this idea, revealing streams of gas trailing behind the galaxy like cosmic tendrils, as if it's still moving through whatever medium caused the warp in the first place. The implications ripple far beyond this single galaxy. If intergalactic gas or dark matter can leave such visible fingerprints, it means the space between galaxies isn't as empty as we once thought. Instead, it's a dynamic, interactive medium capable of shaping the very structures drifting through it. Every subtle curve in NGC 1300's disk isn't just a flaw. It's a message written in the language of gravity, waiting for us to decode its secrets. In every corner of the universe, large galaxies like NGC 1300 should be surrounded by entourages of smaller satellite galaxies, cosmic minions orbiting their massive hosts like bees around a hive. The prevailing lambda-cold dark matter model, our best blueprint for how the cosmos evolved, predicts this hierarchy with mathematical certainty. Yet when astronomers scan the skies around this sprawling spiral, they find something startling: silence. Where there should be dozens of dwarf companions, there's only a handful at best, and even those are strangely faint. This cosmic vanishing act isn't just a curiosity, it's a direct challenge to our understanding of how galaxies form, and it might force us to rewrite the rules of the universe itself. The mystery deepens when you consider the numbers. Simulations based on the lambda-cold dark matter framework suggest NGC 1300's gravitational pull should have captured at least 30 to 50 dwarf galaxies over its lifetime, each containing millions of stars. Instead, fewer than 10 have been detected, and most of these are so dim they skirt the edge of observability. It's as if someone selectively erased the galaxy's cosmic retinue, leaving behind only the faintest whispers of what should be a bustling stellar neighborhood. So where are all the missing satellites? One leading theory points to a dark matter discrepancy. The lambda-cold dark matter model assumes dark matter is cold, slow-moving and clumpy, forming invisible scaffolds where galaxies assemble. But if dark matter behaves differently, then we think perhaps warmer, faster, or more diffuse. It might not clump finely enough to birth the expected swarm of dwarfs. Alternatively, the missing satellites might exist but are too dim to spot, their stars scattered by eons of tidal forces or smothered under thick veils of interstellar dust. Some astronomers argue we're only seeing the survivors, their brighter siblings long since devoured by NGC 1300's voracious gravity. Then there's the wild card: reionization. In the universe's fiery infancy, intense radiation from the first stars and galaxies could have sterilized smaller proto-galaxies, stripping away their gas before they had a chance to shine. If true, NGC 1300's missing satellites might be cosmic stillbirth structures doomed before they ever fully formed. Supporting this idea are the dwarf galaxies we do see. They're overwhelmingly old, their star formation snuffed out eons ago, as if they were the rare few that slipped through the early universe's radiation gauntlet. Yet the most provocative explanation challenges the very foundations of cosmology. What if the lambda-cold dark matter model, for all its successes, is missing a crucial ingredient? Some theorists propose tweaks dark matter that interacts with itself, or even hidden forces between dark particles that could suppress dwarf galaxy formation. Others suggest gravity itself might operate differently on galactic scales, a radical idea that would upend Einstein's legacy. Every undetected satellite around NGC 1300 isn't just an observational gap, it's a potential crack in our cosmic rulebook, urging us to look deeper and question harder. This isn't just about one galaxy's loneliness, it's about the universe's hidden blueprint. If NGC 1300's missing satellites stem from flaws in our models, the implications ripple across cosmology. Galaxy formation, dark matter's nature, even the fate of the cosmos all hang in the balance. Until we solve this puzzle, every silent patch of sky around this spiral remains a challenge, written in the language of absence, waiting for us to decode its secrets. Nestled within one of NGC 1300's spiral arms, an invisible storm rages, a concentrated deluge of cosmic rays bombarding the galaxy with no discernible source. These high-energy particles, mostly protons and atomic nuclei traveling at nearly light speed, typically originate from violent events like supernova explosions or colliding neutron stars. Yet scans of this region reveal none of the usual suspects: no shattered stellar remnants, no swirling accretion disks, just an eerie, unexplained torrent of radiation, as if the universe itself has torn open a hidden fire hose of energy. What makes this cosmic ray hotspot so baffling isn't just its intensity, it's the precision of its location. Most cosmic ray sources scatter particles chaotically, their origins blurred by magnetic fields that twist particle trajectories into tangled knots. But here, advanced detectors have traced the rays back to a surprisingly compact zone, no larger than a few light years across. It's like hearing deafening applause in a pitch-black theater, only to realize the sound is coming from a single, unoccupied seat. The leading theory, a dormant quasar, its active galactic nucleus switched off so abruptly that the shockwaves from its final outburst are still echoing across space, accelerating particles long after the central engine has gone dark. Yet the plot thickens when you examine the ray's composition. Unlike typical cosmic rays, which carry signatures of stellar nucleosynthesis, these particles are laced with rare isotopes usually forged only in the most extreme environments, perhaps even primordial black holes evaporating via Hawking radiation. Some researchers speculate this could hint at exotic physics at play, like quantum tunneling through space-time foam or the decay of hypothetical dark matter particles. Others point to the galaxy's distorted magnetic fields, suggesting their unusual geometry might act like a natural particle accelerator, revving cosmic rays to energies beyond what conventional mechanisms can explain. The implications ripple far beyond this single anomaly. If nature can produce such intense particle beams without the usual cosmic factories, it could mean our detectors on Earth have been misattributing the origins of ultra-high-energy cosmic rays for decades. Every unexplained particle from this hidden accelerator isn't just a scientific curiosity, it's a potential key to unlocking new chapters in astrophysics, reminding us that even in a well-mapped galaxy like NGC 1300, the universe still holds cards close to its chest. NGC 1300 has a thermal secret, dust that glows hotter than it should, radiating infrared light with an intensity that defies all expectations. In most galaxies, interstellar dust absorbs starlight and re-emits it as gentle infrared warmth, like asphalt cooling after a day in the sun. But here, vast clouds of dust blaze with the heat of a cosmic forge, their temperatures soaring hundreds of degrees higher than models predict. No known stars shine brightly enough to explain this fiery glow, leaving astronomers to wonder what invisible furnace is cooking these dust grains to such extremes. The anomaly first became clear when telescopes like the Spitzer Space Telescope and the James Webb Space Telescope mapped the galaxy's infrared emissions. Instead of the expected diffuse warmth, they spotted concentrated hotspots patches where dust temperatures spiked as if doused with invisible flamethrowers. These regions don't align with visible star clusters or supernova remnants. In fact, some of the hottest dust lingers in seemingly empty voids, far from any obvious energy source. It's like walking into a room where the walls are scorching hot, yet there's no fire in sight. One radical explanation points to hidden black holes, not the supermassive one at the galaxy's core, but smaller, intermediate mass black holes, cosmic middleweights that might be lurking undetected in the spiral arms. These stealthy predators could be heating the surrounding dust with their accretion disks, their X-rays absorbed and re-radiated as infrared. Another theory invokes dark matter once more, suggesting certain types of particles might decay or collide, releasing energy that heats the dust like a slow-burning fuse. But the most tantalizing possibility involves magnetic reconnection, a process where twisted magnetic field lines snap and release explosive energy. NGC 1300's tangled magnetic fields could be acting like cosmic spark plugs, creating microflares that superheat dust without the telltale glow of stars. It's a phenomenon we've observed on the Sun, but never at this scale. If true, it would mean magnetic chaos alone can cook a galaxy's dust to inexplicable temperatures. The implications stretch beyond astrophysical curiosity. Dust temperature isn't just a detail, it shapes how galaxies evolve. Hotter dust alters how gas cools and collapses, potentially stifling or accelerating star formation in ways we've never accounted for. If hidden forces are tuning NGC 1300's thermal dial, we might need to rethink how energy circulates in spirals altogether. Every unexplained infrared photon from this galaxy isn't just wasted heat, it's a clue hinting at processes that could be rewriting the rules of cosmic chemistry in plain sight. NGC 1300's outer halo holds ghostly clues to its violent past, delicate stellar streams arcing through the darkness like celestial graffiti. These tidal tails, the shredded remains of smaller galaxies torn apart by gravity, should tell a straightforward story of past collisions, yet something's amiss. The streams curve in all the wrong directions, their trajectories mismatched with every known model of galactic mergers. It's as if the galaxy's history has been rewritten by invisible hands, leaving behind stellar breadcrumbs that refuse to form a coherent trail. Take the longest of these streams, catalogued as TT16. Most tidal tails trace graceful arcs pulled into alignment with their host galaxy's rotation by eons of gravitational drag. But TT16 kinks abruptly halfway along its length, doubling back on itself like a frozen lightning bolt. Simulations struggle to recreate this path. No single merger event produces such contortions unless the devoured galaxy was moving at impossible speeds or was itself locked in a complex dance with unseen partners. Some astronomers suggest this could be evidence of a rare hierarchical merger, where NGC 1300 consumed not just one dwarf galaxy, but a pair already orbiting each other, their mutual gravity twisting the debris into this cosmic knot. Then there's the matter of metallicity. Stars in tidal streams typically mirror the chemical fingerprints of their parent galaxies. Yet spectroscopy reveals wild variations along these streams. Patches of metal-rich stars alternating with pristine, ancient populations, as if multiple galactic victims were shredded and braided together like strands of cosmic DNA. The most perplexing section, near TT16's base, contains stars with heavy elements usually found only in galaxies 3 times NGC 1300 size, hinting at a lost giant whose existence defies current models of galactic growth. The real enigma lies in the stream's distribution. Instead of fanning out evenly around the galaxy's perimeter, they cluster on one side, as if a cosmic current swept them into a pile. This lopsidedness aligns eerily with NGC 1300's warped disk and lopsided dark matter halo, suggesting a shared origin. Perhaps an ancient collision with an unseen intergalactic gas cloud, or even a concentrated river of dark matter, not only bent the galaxy but also herded these stellar streams into their peculiar configurations. What makes these orphan trails so pivotal isn't just their strangeness, it's what they imply about galactic archaeology. If tidal tails can't be trusted to chart a galaxy's mergers, we might be misreading the histories of countless spirals. Worse still, their chemical mosaics suggest galaxies grow through processes far messier than the tidy, hierarchical mergers our simulations predict. Every twisted strand in NGC 1300's halo is more than a relic, it's a challenge, forcing us to reconsider how the cosmos builds its grandest structures, one violent embrace at a time. Amid the swirling dance of billions of stars in NGC 1300, one rebel streaks across the cosmos at a speed that defies comprehension. A hypervelocity star racing outward at nearly 2 million miles per hour, fast enough to cross the distance from Earth to the Moon in under 15 minutes. This isn't just a star moving quickly, It's a celestial projectile flung from the galaxy with such violence that it's destined to escape into the void between galaxies, never to return. The energy required to accelerate a star to these velocities is almost unimaginable, equivalent to the force of 1,000 supernova channeled into a single, precise kick. But what cosmic slingshot could possibly launch a star this fast? The prime suspect, a lurking binary black hole system at the galaxy's core. Most large galaxies host a single supermassive black hole, but simulations suggest NGC 1300 might conceal a pair, two gravitational titans locked in a lethal waltz. When a star ventures too close to this duo, the chaotic gravity can fling it outward like a stone from a catapult. Here's how it works. As the star approaches, one black hole grabs it, swinging it around like a hammer throw before the second black hole's gravity rips it free at a fraction of light speed. The process, called the Hill's mechanism, is one of the universe's most efficient particle accelerators, turning stars into interstellar comets. Yet this hypervelocity star's trajectory tells an even wilder tale. Unlike most runaway stars which shoot out along predictable paths, this one angles sharply away from the galactic plane, as if something shoved it sideways during ejection. Spectroscopy reveals another oddity. Its outer layers are rich in heavy elements like carbon and oxygen, suggesting it was torn from the heart of a dense stellar nursery rather than a quieter region of the galaxy. Some astronomers argue these fingerprints point to a more exotic origin. Perhaps the star wasn't ejected by black holes at all, but by a close encounter with a rogue intermediate mass black hole drifting through the spiral arms, a dark predator we've yet to directly detect. Tracking this star's path backward leads to another revelation. It didn't originate from the galaxy's center, where the supermassive black holes reside, but from a region near the base of one spiral arm. This raises the provocative possibility that NGC 1300's core isn't the only place capable of hurling stars into exile. Could there be other gravitational monsters hidden in its disk, or did some unprecedented event, like the collapse of a dark matter clump, provide the necessary kick? The star's very existence forces us to reconsider what lurks unseen in this galaxy's depths. The implications stretch far beyond one runaway star. Hypervelocity stars are cosmic messengers, their trajectories encoding secrets about the environments that spawn them. If this one truly came from a binary black hole system, it confirms NGC 1300's core is far more dynamic than its quiet exterior suggests. And if something else launched it, that opens the door to entirely new classes of high-energy phenomena waiting to be discovered. As this stellar outlaw barrels through the void, it leaves behind more than just light. It carries a challenge written in the language of motion, daring us to decode the invisible forces shaping galaxies from within. Hidden in the gravitational whispers of NGC 1300, astronomers have stumbled upon clusters that refuse to shine, dark congregations of mass detectable only by the way they warp spacetime around them. These phantom clusters exert undeniable gravitational pull, sculpting the orbits of nearby stars and bending passing light. Yet they emit no starlight, no radio waves, not even the faintest infrared glow. It's as if the galaxy has woven invisible knots into its fabric, gravitational anomalies where something massive lurks in perfect darkness, the leading theory. These could be remnants of failed galaxies' stellar nurseries that never quite ignited. In the early universe, vast clouds of gas collapse under gravity's pull, sparking the birth of stars. But if a cloud lacked enough regular matter to ignite nuclear fusion, it might have coalesced into a shadowy structure of cold hydrogen and dark matter, a ghostly echo of what could have been. Alternatively, these clusters might be pure dark matter halos, dense enough to bend light but devoid of the baryonic matter needed to shine. Imagine a city skyline at night where one towering building absorbs rather than reflects light, an architecture of negative space. Yet their strangest feature isn't their darkness, it's their resilience. Normally, gravitational disruptions from a spiral galaxy's rotation should tear such clusters apart over eons. Yet these persist, their gravitational signatures sharp as knife edges. Some researchers suggest they might be anchored by intermediate mass black holes, invisible sentinels holding the clusters together through sheer gravitational might. Others propose their evidence of a darker, more exotic physics, perhaps dark matter interacting with itself through unknown forces, forming stable structures that defy conventional models. The implications are profound. If these clusters are dark matter fossils, they could reveal clues about how galaxies like NGC 1300 assembled their halos in the cosmic dawn. And if they're failed galaxies, that would mean our universe harbors entire populations of shadowy counterparts to the luminous structures we see, a hidden architecture woven into the cosmos waiting to be mapped. Every unseen knot in this galaxy's gravitational web isn't just a mystery. It's a doorway to rewriting our understanding of how darkness shapes the light. Buried in the observational records of NGC 1300 lies a sequence so bizarre it defies astronomical odds: 7 supernova detonating within a mere 5-year window, clustered in a single spiral arm. Statistically, a galaxy this size should experience roughly 1 supernova per century. Yet here, stellar cataclysms erupted like cosmic popcorn, each explosion separated by weeks rather than generations, as if some unseen force had flipped a switch commanding stars to die in unison. The odds of this happening randomly are astronomical, literally. Simulations suggest the probability of 7 supernova igniting independently in such rapid succession is less than 1 in 10 billion. This isn't just coincidence, it's a pattern screaming for explanation. The supernova themselves add another layer of intrigue. Spectroscopy reveals they weren't uniform. Some were type Roman II, the violent deaths of massive stars, while others were type Ia, thermonuclear explosions of white dwarfs. Normally, these events stem from entirely different stellar processes, yet in NGC 1300, they unfolded as if choreographed by the same cosmic conductor. One radical theory points to a chain reaction triggered by gravitational resonance. The galaxy's central bar might act like a tuning fork, sending waves of compression through the spiral arms. These waves could destabilize stars already teetering on the edge of collapse, nudging them toward catastrophe in synchronized succession. Picture dominoes stacked not in a line, but across an entire city block, yet when one falls, they all topple in eerie unison. Supporting this idea is the supernova's spatial alignment along a precise arc, tracing what could be the crest of a gravitational ripple frozen in time. But there's a darker possibility: stellar vampirism on an unprecedented scale. If a rogue black hole or neutron star plowed through this region millions of years ago, its gravity could have stripped material from nearby stars, leaving their cores unstable. Over time, these wounded stars might have reached critical failure points in rapid sequence, like time bombs set to the same countdown. Infrared images reveal faint scars in the interstellar medium, telltale trails of disturbed gas that could mark the predator's ancient path. The implications rewrite our understanding of stellar life cycles. If supernova can be synchronized, entire spiral arms might experience waves of star death that reshape galactic chemistry in sudden, punctuated bursts rather than steady drizzle. Every unusual isotope ratio or unexpected dust cloud in NGC 1300 could bear the fingerprints of this apocalyptic parade. And if external triggers like passing black holes are to blame, it suggests galaxies aren't just isolated islands, they're dynamic battlegrounds where invisible invaders can orchestrate stellar demise on a scale we're only beginning to comprehend. This isn't merely a record of destruction, it's a cosmic puzzle box. Each explosion in that fleeting 5-year window wasn't an end, it was a clue, hinting at forces that weave through galaxies like invisible threads, pulling stars toward oblivion in rhythms we're just learning to hear. Among the 30 enigmas of NGC 1300, none unsettles the foundations of physics quite like the whispers of quantum entanglement echoing across 65 million light-years. Astronomers have detected eerie correlations between photons arriving from opposite ends of the galaxy, particles of light, that seem to mirror each other's properties instantaneously, as if connected by an invisible thread defying the speed of light. In the quantum realm, such entanglement is commonplace, linking particles across lab benches, but witnessing this phenomenon on galactic scales, that shouldn't be possible. Yet the data persists, revealing photon pairs whose polarizations align with odds exceeding random chance by factors of billions. The implications are staggering. Quantum entanglement relies on particles sharing a unified quantum state, a connection so intimate that measuring one instantly determines its partner's fate, no matter the distance. But this spooky action at a distance, as Einstein called it, was never meant to survive the harsh realities of interstellar space. Cosmic radiation, magnetic fields, and gravitational tides should decohere these delicate quantum states long before they span a galaxy. That these correlations endure suggests something extraordinary. Either space-time itself preserves quantum links in ways we've never imagined, or NGC 1300 harbors a mechanism actively reinforcing entanglement across unimaginable scales. One radical theory points to the galaxy's lopsided dark matter halo. Certain models of dark matter propose it could interact through exotic quantum fields, creating a background network that sustains entanglement like a cosmic telephone line. If true, photons traversing these regions might imprint their quantum states onto the dark matter medium, which then relays the information to their partners, effectively cheating the speed of light limit. Others speculate the galaxy's quiet central black hole plays a role. Its unnervingly stable event horizon might act as a quantum gate, entangling particles that pass on opposite sides before flinging them outward like a subatomic version of Newton's cradle. Yet the most controversial interpretation challenges relativity itself. Could these photons be revealing a deeper layer of reality where entanglement isn't bound by spacetime's rules? Some theorists suggest the correlations stem from retrocausality, future events influencing the past, or even holographic principles where the galaxy's 3D structure encodes quantum information on a 2D boundary. It's as if NGC 1300's photons are tapping into the universe's source code, bypassing conventional physics altogether. Skeptics argue the signal is mere cosmic pareidolia, a statistical fluke amplified by confirmation bias. They point to potential instrumental artifacts or unaccounted interstellar effects that might mimic entanglement. But with each new observation, the anomaly grows harder to dismiss. If validated, this quantum whisper could force us to rewrite physics textbooks, proving that the universe's spookiest phenomenon isn't confined to lab experiments, it's woven into the fabric of galaxies themselves. Every correlated photon from this distant spiral isn't just a curiosity, it's a cipher waiting to reveal whether entanglement is the universe's secret language spoken in the dark. From phantom spiral arms to hypervelocity stars, from quantum whispers to dark matter's hidden architecture, NGC 1300 isn't just a galaxy, it's a cosmic hall of mirrors reflecting back questions we're only beginning to ask. Over 30 inexplicable phenomena, each one peeling back another layer of what we thought we knew about the universe. The vanishing hydrogen, the silent black hole, the rebellious dust lanes, they're not just quirks. They're cracks in the foundation of astrophysics, each one hinting that galaxies might dance to rhythms we've yet to hear. Take the starburst paradox, where stars ignite in chaotic bursts against all odds, or the missing satellites that defy dark matter's predictions. Even the way this galaxy's bar spins flawlessly for billions of years longer than it should, as if gravity itself has bent the rules. And who could forget the entangled photons, threading quantum weirdness across 65 million light-years? Every anomaly in NGC 1300 is a breadcrumb on a trail leading to something bigger, something that could rewrite textbooks. But here's the real marvel: this galaxy isn't just an outlier. It's a mirror. What we learn here echoes across the cosmos, forcing us to reconsider how black holes feed, how stars form, even how time flows. Maybe the universe isn't as orderly as we thought. Maybe the rules are just suggestions, and galaxies like this one are the exceptions proving it. So now it's your turn. Which of these 30 mysteries lingers in your mind? The Phantom Supernova that left no corpse, the warped disk bending under invisible hands, or something else entirely? Drop your thoughts in the comments. We're all detectives in this cosmic mystery. And if you're hungry for more deep space enigmas, hit subscribe. The universe is stranger than we imagine, and together we're just starting to explore.